So good morning to everyone. First of all, some information about the collaboration that Bethe-Salpeter is so important to obtain optical properties. First of all, we are since it is an initial approach that how not only to calculate the optical properties and to reproduce experimental data without, in principle, any parameter, but it's also able to explain the optical properties, interpret the experimental results. And since it is in the framework of a mixed method that is able also to predict the properties, the optical properties of new material, in this sense, it can be interesting also to interpret the phenomena related to optical devices, for instance. And so, means that it is very important to have an interpretation of the optical properties for a lot of phenomena like photocatalysis, photovoltaics, photochemistry, LED, laser, and so on, where optical excitation are the key role of this phenomenon. So let me go to the outline of the talk. First, I will try to give you a reminder of what we have learned up to now. Then we go to the derivation of the Bethe-Salpeter, try to understand which are the key physical phenomena related to it. If I have time, I will go through the relation of the Bethe-Salpeter with the spin degree of freedom and try to understand how the Bethe-Salpeter there are problems with the slide that goes I don't want. Okay, the spin, finally, I will give you some examples just to give you an idea of the results, but you will see much better in the tutorial. Okay, so first concept that you should be aware is the fact that already has been told by several speakers that neutral excitation and charge excitation are different. So when you measure excitation, actually in the experiment you do photoemission, inverse photoemission, so you can obtain an electronic gap or scanning spectroscopy. This is the electronic gap. While when you measure data like absorption, reflection, transmission, also photoluminescence, but it's much more complicated to deal with since it is an out-of-equilibrium phenomenon, so I will not speak about photoluminescence. In any case, in this case, what you measure is actually neutral excitation. So it's completely different, and this is a key concept since in some material, especially low dimensional material, the material where the screening is very low, I'll show you in a minute, the electronic gap and the optical gap can be very different, okay? So this is one concept that you have to remember. The other things that we have learned yesterday ago with Helena is the fact that I already proved yesterday in the tutorial is that we can calculate the optical properties at the independent particle level, and this is the equation. Normal physical rule that you know from quantum mechanics. You know that the transition are independent particle transition, and you can calculate the optical spectrum, but in many cases, like here, you see that the agreement with the experiment by silicon, even if you correct the gap with GW, is not good. So the experiment is not, and the theory do not agree. Even worse is the situation of material like fluoride, where you know the Wi-Fi insulator, the electronic screening is very small. And if you compare experiment and theory at the GW level, are completely off here, and the WF is this one, the experiment is this one, this is the independent particle G level. This is a 2D material, what is done is fine again, completely different independent particle GW and experiment. So must be clear that we are missing some. Which are the physical materials that we are missing? So now I want to discuss this. Okay, first of all, the concept already given by Helena, the fact that we already yesterday in the tutorial, the fact that the local effect is an effect that you have to deal with. And this is why even if you apply an electric field that is macroscopic, the perturbation is macroscopic, in your material you have fluctuation of the density that are microscopic. So you have to deal with this and take average, as has been shown by Helena, and then you have actually the fact that you have to average these two quantities, you can factorize, and at the end, the macroscopic, the electric function is nothing else than the average of the microscopic inverse, the electric function. And this is the equation that yesterday you applied in the second tutorial. So you have to take into account the fact that local field in general have to be included if you want to calculate a macroscopic quantity. And this is what you want to do, okay? And again, if you include the local field effect, this is not solved the problem. You are still missing something. The agreement with and without is not good with the experiment. Again, silicon. So, okay, before giving, so we have to local field effect. Let me give you another formulation, mathematical formulation of local field effect that is used in the solution of the Bethe-Salpeter, that, as you see, includes the local field effect naturally. What can be demonstrated is that instead of doing this inversion here, as shown by Helena and mentioned by me, what we can do is calculate where there's an equation in the free space where we include, instead of having, this is the normal equation, that's an equation, the reducible polarizability and the reducible one, we can define a Coulomb potential that we call V bar, where we put to zero the long range component. Now, it can be shown mathematically, you can find the derivation here in this paper, that in order to include the local field effect, instead of using this formula, you can use an equation, and that is an equation for a P bar, where instead of having the full Coulomb potential here, you exclude the long range part. This can be proved mathematically that you can obtain the macroscopic, the electric function directly taking the head of that P bar, okay, without doing the inversion. So now keep in mind this. So we want to include the local field effect. Okay, but this is not the end of the story because they are not enough. So what we have to do is actually to include another physical effect, which is the physical effect. The physical effect is related to the fact that when you excite the material in absorption, for instance, what you do is not create a charge excitation. So you are not taking out the electron from the system or adding the electron to the system, but you create neutral excitation that are electron-hole coupled that fill each other. And so the physical effect is that, as you will see, you create two different phenomena. One is the fact that actually you have a normalization of the intensity of the peak with respect to independent particles. This is what we call continuum resonance, continuum exciton, whatever it is. And then, more importantly, in many materials, not all, what we will see is that you are able to obtain bound exciton. Bound exciton are actually peak that you see below the electronic gap, that you can never include at one particle level. So what we will try to see now is how to include these two physical phenomena. What we will see at the end is that what we have is that at the end, the absorption that we will obtain is similar to the independent particle one, but is profoundly different because here are dipoles that are excitonic dipole that we will see can be obtained through the diagonalization of what we call an excitonic Hamiltonian. Physically, an excitonic Hamiltonian is the fact that we are able to rewrite the equation we will see for the polarizability in terms of this Hamiltonian that describes physically the interaction of an electron through the Coulomb potential, the Coulomb interaction that is screened. And so, as you will see here, the peak are renormalized, the independent particle dipole, that is the same that we have seen yesterday in the formula before, are renormalized by the eigenvector of this excitonic Hamiltonian. That is what Young solved, and then you can calculate the vector. So now we have to understand how to teach this equation. Okay. So the idea, the physical idea, is that so you should have understand that the K quantity that we are dealing with is the polarizability. The polarizability is what we want to calculate, but we have to go beyond the independent particle propagator, because we have to deal physically with the interaction that the electron and hole with each other when you excite the system. So sorry, what we have to do is try to go beyond the independent particle level and try to include the interaction, and as you will see, means to include in the equation the gamma vectors. And this will give us, as you show in the next slide, the equation for the correlated propagation of electron and hole through the interaction. Okay? And okay, so let me go further. In the next seminar, Davide will present something related to non-equilibrium dynamics, and so probably we will introduce again one of the possible derivations of the Bethe-Salpeter related to non-equilibrium dynamics. But let me go to other two possible derivations of this equation. The mathematics is quite long, I try to give you an idea, but you can find the things in these two references. First of all, okay, as I told you, you should have understand that there is one possibility is to go directly through the equation, or derive a second possibility that I try to mention is to go, to derive the same Bethe-Salpeter equation through a generalization of the dielectric function in the linear response, introducing a generalized 4-point equation. Let me come back later on this. Okay, so come back to the first. Already yesterday, several speakers have mentioned the eigenequation that is represented by this pentagon. To understand that is equation, integral differential equation related, and you have to solve them consistently. What we have done yesterday is assume that the gamma vertex at the beginning is 1, and then we stop. We have discarded the equation in a very compact way. And then we assume at the beginning that the gamma is delta, and then we do a cycle and we obtain GW. Okay, so what we can do is do a second iteration and try to see what we can obtain for the pi at the second iteration, p at the second iteration. So if we do this, we continue, we assume that sigma, the self-energy, is EGW. Then we obtain that gamma is this equation, and then we can calculate the functional derivative of the self-energy. And so in principle, we have two terms, but several others, and also because numerically it's very complicated, what we do normally, and you will prove in the Bethe-Salpeter solution, is to neglect this term. So we assume that this term is null. So the functional derivative of the self-energy is simply W. And then we have an equation for gamma at the second iteration, that is delta delta EW GG gamma. In a common way, I didn't put the explicit dependence from space and time. So now we are ready to see what is the polarizability when we define gamma at the end of the first iteration. Then what we can do, we can calculate the irreducible polarizability, including gamma, simply taking the equation for the vertex and multiplying by GG. And then actually what we have is an equation for a 3-point polarizability where the gamma beyond delta delta is included. So we are into the diagrams beyond the fact that the two electron hole propagator are independent. And so we have this equation. And then finally, what we can do is open this point here to two different points. And you see here, you have a correlator, a polarizability that here I call P tilde, that are the two independent propagator with this, again, the same equation. This is the correlator, the P tilde, and this is the interaction that is W, the screened Coulomb potential. For time means that here you have the dependence of two positions in space and time, two positions in space and time. This is the equation. And what we do, so here, what we can say is that 4-point generalized equation for the polarizability. Okay? Now, what we do to obtain the Bethe-Salpeter is that the fact we want to move from the irreducible polarizability that we obtain from frame diagrams to the reducible polarizability that is connected with the experimental observable. And so we can connect the two, and you obtain at the end, obtaining this, substituting in this equation, at the end you obtain an equation for the P bar. But remember, P bar is the quantity that I defined at the beginning of the quantity that gives me directly the macroscopic electric function. And so now we have the equation that is actually the Bethe-Salpeter equation for the polarizability. Once we have this, we can have directly the macroscopic electric function. So now we have to understand how to solve this explicitly. So what we can say is that this is the P0, the independent propagator, calculated at the end of the first cycle means not DFT but zero. 0, so by 0, P, this first term is the independent propagator, while the other two are what we call, sorry, I have a problem with this. This is what we call the excitonic kernel. Okay, this is the electron hole propagator, and this other term is the excitonic kernel. That describes the fact that the two propagator, electron and hole, are not independent but interact through different kind of diagram. In our case, we arrived to two terms, that is V bar, the Coulomb screened potential without the G equal to 0 term, and W, that as you see, one is, you say, repulsive, the other is attractive. Minus W means that the electron hole wants to stay hardbound in some sense. Okay, can create exciton. So the first one is what we call electron hole exchange. Okay, that is a sense repulsive, and since we include V bar, we are including a naturally local field effect, while the other is attractive. But as you see, I mean, probably you don't know, they are not, I mean, they are not of the same kind. You see, the index are not the same. So the aromatically, they are not exactly the same, and this is the reason why Bethe-Salpeter is so difficult to be solved with respect to the independent DFT approach. That is not the story. Okay, so one approximation that we normally do, all code do, is assume another things, is the fact, okay, P0 is calculated P0 W0, that is what we have seen until now theoretically. Then what we have done, we neglect the dependence of W from G, the second term in the functional derivative, and we do another approximation that we assume, in principle, we have this kind of interaction, depends from two positions in R, R prime, T prime. But what is generally done is the fact that the interaction is static. So in the Bethe-Salpeter, the kernel is only the static interaction of omega equal to 0. Okay, this is another approximation. There are attempts to go beyond. There are several papers. I put other reference beyond this at the end of the seminar. Okay, so this is the first. So the K idea is that we have to go beyond the first cycle and include the gamma vectors in the equation, and we have to deal with the polarizability. So another way to see this the same physical phenomena, let's say, is to deal directly with functional derivative in the term of linear response. As you know, already seen in the first lecture, the linear response, the chi, is related to the functional derivative of the density with respect to the external potential. Okay, we have seen in the first lecture, and this is what we have used up to now. But in the many body green function approach, we know also, and they have shown, that the density is also defined in the term of the green function in this way. So what we can do, and actually is what I will do now, is define a 4-point correlation function that you see is a generalization of this equation with 4 points in space and time. You see, it's exactly similar, but we are including an external potential that is a generalization, is a non-local in space and time. Okay? If you do this, then you can recover the normal chi simply considering the same point at the end or at the beginning. Okay? So let's see how to derive the same equation that I'm obtained now. If you start with this L that is defined by this functional derivative, that you know that this equation is true, the functional derivative of gg minus 1 is equal to 0, then with a few mathematics you can demonstrate that also this formula is true. And then instead of having this equation, you can substitute this in this equation here. Okay, so it's simply, you have to do these two passages and you arrive to this. Okay, then when you have this, what you can do is remember the Dyson equation. We know this is another form to write the Dyson equation, and the g minus 1 is g0 minus 1 minus this term. Consider that here is the external potential that we introduced in the theory, the functional derivative, and this is sigma, where sigma is the correlation, the exchange correlation part that here I call the sigma, the tilde, and also the R potential. So everything beyond the real independent problem, non-interactive problem. So if you consider this and substitute to g minus 1 the equation that I showed before, you can do the functional derivative, and then clearly g0 does not depend from this external additional potential that I included, so I can neglect. This term is a delta, and then what we obtain, if I'm able to go, is that the equation again gives you an L0 and this term here. And then, if you see again, we have a functional derivative. You can apply the chain rule for functional derivative. And this is a 4-point equation, the functional derivative of the self-energy with respect to G. And this is again what we have defined is the L correlation function. And so at the end, the same story, you can, I have a problem. Okay, so if you apply the functional derivative to the two terms, what we see is that we have now again two terms. One that is the functional derivative of the R potential with respect to G. That is what in the previous derivation I mentioned is the electron exchange term. That actually in this derivation you see is the functional derivative of the R potential. Okay, and the other part is the functional derivative of the exchange correlation self-energy with respect to G. That again give you the same formula that we have seen before, since we neglect the dependence of W from G like before. And so at the end, actually we are obtaining exactly the same equation. We can define the equation for the two-particle correlation function. So this is formally the two-particle Green function minus the uncorrelated propagator for the electron and hole. And at the end, diagrammatically, is exactly the same. So we have, this is the L, L0, that is independent particle propagator, 2. And then we have again the kernel here that is given by these two terms. Okay? That again are not, you see, the index are not the same. Okay? So now, this is the equation. So now, how is solved this equation practically? What the young Godard told the code do generally is that what we do is try to rewrite the equation in the transition space. Because generally, if you think when you want to describe the optical properties of material, not all the transitions are possible. Maybe you are interested in the transition in a certain region near the earth or in some part of the spectrum. So, if you can typically restrict the number of transitions involved, instead of solving that equation in real space and time, that is an equation for 4 points, what we do is try to remark the equation in the transition space, how it is done. What you can do generally if you have a function of 4 points, like our P bar, we have an equation of 4 points in space and time. 1, 2, 3, and 4 means the equation in space and time. Also spin about space and time, each of these 4 points. What we can do, when I say rewrite things in transition space, we can do mathematically this equation. So we can write, let's say, the polarizability, what we will do now. Instead of in terms 1, 2, 3, 4, we can do an integral in the 4 variable for the states that in our case are the connection states, okay? That are equal to the quasi-particle state for the absorption function that we have done yesterday. Okay, so what I'm saying is that now we rewrite everything in terms of transition space. So T for me is the index that couple connection state from N1 to N2, a transition from N1 to N2, and the same for T prime, N3 and 4. So what I'm trying to show you now is how the equation for the P bar appear in the transition space. And then we will see that is actually this excitonic Hamiltonian that I introduced before. Okay? So let me go, I mean, I skip all the passages, but if you do this, you are able to write the equation from the P bar, that you remember is in terms of P0 and the kernel. If you do all the mathematics, what you see is that actually you can rewrite the equation for P bar in this transition space in an equation like that, where these are the Fermi occupation of the states N3 and 4. And here in the denominator, you have an equation that you see is a resolvent. So this is an excitonic Hamiltonian that has, now I will comment on that. But in any case, this is the inverse that depends from omega only externally. So this equation does not depend from omega because we eliminated all the dependence from omega since we assume that the kernel W is static. Okay. And so we have this equation and the excitonic Hamiltonian. So now try to understand which are the terms. As you see, the excitonic Hamiltonian depend from the index of this transition space that are the connection state. So we have a term that is the diagonal part of the excitonic Hamiltonian. And you see here, this is again what we call before the kernel that is composed of two terms, the W minus W, that is the spin and the electron hole attraction, and V bar, that is what we call the electron hole exchange. And if we put bar, we obtain directly the macroscopic dielectric function. That is what normally you want to have for absorption. Okay? And so, okay, you can explicitly see how the equation looks like, assuming that N1 and 2 can be of different type. It can be principal C, another one here I call C or bar, the four possibility. And okay, you have this equation, but clearly, okay, please keep in mind that when I call VSC, in principle, if the system is extended, we consider that there is also the index K, okay, the quantum number K. So here I put only V and C just to simplify the notation, okay? And so, but since clearly the epsilon m and the absorption depend on the partition from occupied to unoccupied, a part of this equation does not enter, while, oh, sorry, what? I have to come back. Okay, while the only part that is interesting for us is this one. Okay, you can see that we have the full excitonic Hamiltonian here, while only the kernel remain in the diagonal part. And at the end, what we have is that what is called the excitonic Hamiltonian is this part here, okay, where we have the transition that are VC, V prime, C prime, the opposite, okay, turns out that is the conjugate with the minus sign, and then this part is called the coupling term. Okay, so now what you will do in the tutorial at the end is assume again that this part, the coupling, the non-diagonal part in the transition space is small, and this is generally works well for extended system. For solid, it is very good approximation. It's not so good for molecules or low-dimensional material in some cases. So if we neglect this part, this is called the time-damping approximation. I don't know if any of you have experienced the time-dependent actually functional calculation, but this is the same approximation that they use. And what you will do actually for the calculation that you will do in the tutorial is considering only what we call the resonant excitonic, okay, the resonant part of the excitonic Hamiltonian. Okay, so now let me, I don't have time, unfortunately. It's long, the talk. Okay. To enter in detail, because until now I completely neglected the spin degree of freedom. Okay, so in principle, I have to examine this, including the spin degree of freedom, and we have three possibilities. One, the material is not spin polarized, up and down at the same. One is polarized, magnetic system, and one, if you include spin orbit, each connection state is actually expanding. So you have to deal with this equation in the different possibility. There is some mathematics, but the idea, let me go just to tell you what you will see in the tutorial. If you treat material that are non-spin polarized, what we call collinear case non-spin polarized, let's say silicon, boron nitride, whatever it is, what you can demonstrate from mathematics is the fact, let me go to the hand, that actually when you will solve the equation, you are not actually solving the equation that I showed before, but if you include the spin degree of freedom and you have to deal with singlet, you can separate the space since S squared is the number in non-spin polarized case, you can deal with singlet and triplet state, normal material. And you know that in the spin selection rule, only singlet state can be excited by in the dipole approximation by the light. So what actually you will do when you will do the tutorial is solve an equation where it appears to be beyond beside the exchange correlation part of the kernel, and this is the excitonic Hamiltonian for singlet exciton. Consider that if you want to, for some reason, know which is the triplet first exciton, in some material can be interesting to know the exchange splitting between the two. It can be proved from that for triplet, the Hamiltonian that you have to solve, you have to put to zero this term. It's something that you can do in Yambo, putting the exchange part 0. This is the excitonic Hamiltonian. Okay. You can do more. You can do also spin polarized. In the case of, I don't know if there is a tutorial for molybdenum disulfide. In the molybdenum disulfide spin orbit is very important. So you have to start with non-collinear and spin orbit inside the calculation from the DFT. In this case, the Hamiltonian means that it's not written in terms of scalar connection state, but spinor. It means that you have to do the same derivation, but the equation here is in space is 4 times larger, because for each state you have spinor. So you have double of bands, let's say, when you consider the transition. Okay. So I skip this. Then, when we have this excitonic Hamiltonian, once the mathematics is proved, we have all, because we are actually deal with the fact that we have to invert this equation. So from epsilon m, we know p bar at this point, that is derived dealing with this excitonic Hamiltonian, and then we have to calculate epsilon m. In Yambo, you can do both. You can diagonalize the excitonic Hamiltonian, and means that you can find the eigenvectors and eigenvalues. And then you can analyze also these that want to know exactly which are the level, not only the spectrum, this is what you have to do. There are different approaches to do normal library and also iterative approach, recursive approach, or you can use inversion directly, that is or by LAPACK, ScalaPACK, or by Lenz-Haydock approach. But in this case, you will have not the eigenvalues, the eigenvector of the Hamiltonian, but only the spectrum. Okay? So because you deal directly with the inversion. So you do not diagonalize the Hamiltonian, and you do not use the referent. Okay, so I will skip all the rest because I am in delay. Let me give, some examples that are very old, actually. So this is the first spectrum calculated by Lucia Reining and Albrecht, I don't remember who, Rodolfo maybe. That is in this paper. Okay, here you see when you include excitonic effect in silicon, even if exciton, bound exciton in silicon are not, there are not exciton, but you see the intensity of the peak completely change. Why? Because if you remember the equation that I showed, the dipoles are excitonic dipoles that are a linear combination through the excitonic eigenvector. So the intensity of the peak change a lot, even if the position is already okay with GW. But the position change a lot. While here, the argon solid is a material with a very large gap, so very low dielectric screening. Very low dielectric screening means the W is very important because electrons all feel each other physically really much, while in silicon, due to the polarizability of silicon, no. Okay, so the solid argon, this is the GW gap. If you calculate the independent RPA is the green, while the Bethe-Salpeter perfectly match the experimental data. And this is about that you never be able to obtain with any independent particle calculation. Okay, other example here, quite historical. Let me go to 2D material, like the field where these excitonic calculations are very, very important because all the optical properties of 2D material are related to exciton actually. In many materials, for instance, it's proved experimentally that if you measure the gap in scattering standard spectroscopy is a value, but if you measure with photoluminescence, the peak is completely off from the gap. So means that there is a bonding energy of about 1/2 of electron volt, and this is able with the Bethe-Salpeter to obtain a good agreement with this experimental data, but also you can deal with the exciton in bilayer TMB or charged exciton in organic and inorganic material. Okay, so I have to end. Okay, if you want, we can, I want to show you that in principle, in all material, also to the material, if you want to calculate absorption, no need to go beyond the standard of approximation, but in molecule, instead, it's important to include the other part of the excitonic Hamiltonian that I mentioned in organic material. Okay, this is just a brief introduction of the Bethe-Salpeter. There are many developments in the last year. For instance, there is the possibility to include not only optical properties, but also finite momentum excitons that are important a lot in two-dimensional material, and to obtain exciton at finite momentum. And also it's possible to include the finite temperature Bethe-Salpeter. There are references here. And also, I mentioned the photoluminescence quite often involve the electron phonon or exciton phonon interaction, and it's possible now to calculate the phonon assisted PL spectra. Elena is here, and also Fulvio, our author of this Davide also. So here are all the main reference, and sorry if I was too long. Thanks.